Hello, and thank you for joining me today. My name is Will Cunningham, and I'm the head of quantum software at Agnostic. Today, I'll be discussing high-performance classical quantum workflows with Covalent. Let's get started. You may be wondering, what is a workflow? Most simply, a workflow is a collection of tasks connected by dependency relations. Visually, a workflow is represented by a directed acyclic graph as shown in the picture. In HPC, users may already be familiar with workflows if they use more than one hardware resource in their experiments. For example, a user may perform some data preprocessing on their local laptop, then transfer it to a supercomputer where it is used as an input to a high compute simulation. Finally, results are collected, some post-processing may be performed to remove corrupt or missing entries, and the results are visualized in some plot. In more complex settings, users may be interacting with multiple supercomputing clusters, cloud HPC resources, and now even quantum computers. All of these options together, in turn, mean that scientific workflows can quickly become large and difficult to manage. In the era of hybrid computing, there are more options than ever when it comes to how you interact with HPC devices. Experiments become heterogeneous in so many ways. They can be classical or quantum, use high compute or general compute resources, use cloud or on-prem compute clusters, involve serial or parallel algorithms, and even deterministic or probabilistic algorithms. In reality, we are transitioning to a world where all of these options can be considered together for a single application. It can become very difficult to make sense of so many options. Likewise, as heterogeneous HPC becomes more mainstream in both academic and commercial endeavors, the demand for resources will increase. In today's NISQ era, quantum computers are in high demand, and it is commonplace to wait for hours in queues. Practically, this means both hardware providers and research groups need to be careful about how HPC and quantum reservations are utilized. Quantum computers are expensive, difficult to maintain, and have a relatively short lifetime compared to classical resources. Moreover, with the supply chain challenges faced today, and likely for several years to come, it is not as simple as buying more computers. We must develop software tools which empower both users and providers to more efficiently use existing resources. Suppose that a user is able to overcome these challenges. They get reservations on a variety of resources, design their code in the best way possible, and then start running experiments. Even still, users face a new set of challenges. As soon as multiple hardware resources are introduced, users face problems managing, reproducing, and sharing data. Data can become fragmented across many devices, and it can become challenging to get a view of an entire data set. If data is missing or corrupt, which is common at scale, it may no longer be feasible to generate it on the same hardware as the initial attempt, which leads to further fragmentation. Moreover, if an experiment fails to run to completion, it can be challenging to trace back a failure to its source, especially when multiple devices are involved. Finally, it is quite difficult to convey to peers how to reproduce a dataset when they need information about everything from hardware specifications to runtime environments to input parameters. At present, this burden is squarely on users to solve. At Agnostic, we developed Covalent to overcome these challenges and to empower users to spend more time focusing on research applications and less time on research operations. Covalent makes scientific workflows modular, scalable, and reproducible. With Covalent, users can quickly prototype an experiment, try it out, and iterate using different input parameters, software environments, and hardware resources. Once an application is understood, the results worthy of being saved or published can easily be extracted from the broader dataset and shared with colleagues or moved to a production database. A key feature of Covalent is the ability to execute software on different hardware resources, even in custom hybrid configurations. This is particularly relevant to quantum algorithms, where already users need to pair classical and quantum resources. With Covalent, users can send tasks to HPC clusters, quantum devices, public clouds such as AWS, Azure, and Google Cloud, or even run the tasks locally on their laptops. Covalent allows users to prototype locally and then run tasks at scale somewhere else with minimal change to their software. Covalent is a distributed workflow tool. You may already be familiar with other Pythonic tools lower in the stack used to accelerate your computations. JobLib, Cython, Numba, and PyCUDA can be leveraged to parallelize applications over multiple cores. Likewise, Dask, Rapids, Coiled, and PySpark can be leveraged to distribute parallel applications over multiple devices. Users in HPC may be familiar with the OpenMP plus MPI experience, which achieves the same effect at a more granular level. At the top of the stack, above Covalent, we find commercial workflow orchestration tools such as Prefect, Dagster, Airflow, and Luigi. These tools are used in large-scale enterprise machine learning and data analytics applications where certain tasks must run on a time-based schedule without fail. Covalent sits at a layer in between the distributed computation and workflow management layers, which is why we call it a distributed workflow tool. In Covalent, instances of the workflow, rather than the workflow itself, are the primary objects. This core design principle enables the type of rapid iteration needed for pre-production R&D workflows while remaining compatible with tools at the other layers in the stack. Let's take a quick look at what a Covalent user might experience when getting started. Users can get started in a Jupyter Notebook, which has become the platform of choice for prototyping, especially in high-performance settings. I'll pause here to note that traditional HPC users can still interact with Covalent using standard scripts. The first step users might want to take is to functionalize their existing code. While this is good practice anyways, in that it increases maintainability and code quality, it is required for Covalent as functions are what will be mapped to tasks in a workflow. Next, users can add small one-line decorators to each of their functions. Internally, this converts the functions to callable class objects, which have the ability to save loads of metadata about the function and how it ran. However, these functions remain callable as standard Python functions in the way that you might expect. This differs from some other workflow tools which require the use of YAML rather than Python. Notice we use two different decorators. The electron decorator refers to a task, while the lattice decorator refers to a workflow. These terms are borrowed from condensed matter physics, where groups of electrons can form lattice structures. Next, users can add execution information to the decorators. Executors are used to tell Covalent where and how to run the tasks. Here we show two examples. One uses the Slurm executor, which submits a high compute task to a Slurm partition in an HPC cluster managed by Slurm. The second uses the AWS Fargate executor, which submits a low compute task to the AWS Elastic Container Service, where it can run using AWS Fargate. With these two different executors, a workflow using these tasks can flexibly send tasks to both high compute and low compute resources. Finally, let's turn to the graphical user interface provided with Covalent. Visualization is an incredibly important part of how we understand HPC software and hardware, especially at a time when we're no longer limited to a single supercomputer. In the Covalent UI, you can view task dependencies and their statuses, analyze partial results using native checkpointing, and better understand where time and money is being consumed. Moreover, the large amounts of metadata stored with each invocation means it becomes trivial to reproduce results, regardless of the complexity of the workflow. We believe that these abilities are crucial to research and development, and that they will provide immense benefits to end users and their peers. Let's summarize what we've discussed so far. Covalent supports a variety of hardware compute backends, whether they are in the domain of academic HPC, cloud computing, or quantum computing. Our team is working hard to increase this list to the greatest degree possible. Since Covalent operates a layer above other research software packages, all of the standard data science, machine learning, and quantum computing software toolkits are compatible with Covalent. In other words, Covalent provides a means to interact with these packages more efficiently, especially when there can be version conflicts. We recognize that Python is not the first language of choice for many HPC users. We don't ask that you rewrite legacy code in a new language. Instead, we provide bindings between Covalent and other common HPC languages so that Python is used for orchestration, while C or C++, Bash, Julia, and Fortran are used for the actual compute task. We recognize that this interface is critical for a good user experience, and we welcome feedback from users with novel requirements. To reiterate, the Covalent UI provides a powerful graphical interface where users can interact with their workflows. They can visualize task dependencies, use the dashboard for real-time monitoring, check for status updates, and view the cached inputs and output variables. Covalent provides a unified interface where users can go to map their software to hardware in a straightforward procedure. They can mix and match parameters to rapidly identify the best solution for their particular application. In summary, Covalent makes experiments manageable, scalable, and reproducible. It's fully free and open source on GitHub, so go check it out today and drop us a star if you like what we're doing. Thanks for listening.